Greetings to Dr. Chu Chung Seong, Dr. Matthew Wong, Dr. Chi Mei Yin, and to the other viewers that are watching this presentation. My name is Kelvin Yung, and I'll be presenting my final year research project topic, Evaluation of Silica Manganese Slag as a potential subsurface filter in landfill liner systems. Before we dive into the topic, you must first understand what a landfill is and why there is a need for landfills. In Malaysia, the rapid urbanization and increase in population of the country results in the increase of municipal solid waste. Hence, one of the most common methods of organized waste disposal is with engineered waste control systems known as landfills. According to Muhammad Idris, landfills are highly engineered waste constructed depressions in the ground where municipal and industrial waste are disposed to via containment systems designed to isolate and separate landfill contents from the surrounding environment. As such, landfill liners are critical control strategies that isolate hazardous and municipal solid waste and inhibit the flow of percolated liquids from waste, also known as leachate, preventing infiltration of leachate into the surrounding environment for a long period of time. Typically, the liner system will consist of multiple layers that are stacked in descending order, starting with a filter layer, primary leachate collection and removal system (LCRS), a primary geomembrane, a leak detection collection and removal system (LDCRS), and then a composite liner above the native foundation soil. The figure at the literature review section illustrates the schematic profile of a typical landfill liner, in which I will explain how it is significant in this research project later in the literature review. However, I must first stress the single most important material property of a landfill liner, which is hydraulic conductivity, where typically a composite liner possesses a hydraulic conductivity of 1 × 10⁻⁷. Hence, when considering a particular soil as a lining material, the most critical properties that it must possess is low permeability to prevent the passage of leachate into the soil and groundwater environments. After understanding the schematic of a landfill liner and its most important material property, the motivation of this research plan is the proposal of exploring the potential of upscaling silica manganese slag from waste into construction materials for landfill subsurface materials. So what is silica manganese slag? Firstly, silica manganese slag is an industrial waste or byproduct from ferroalloys production or silica manganese production, where during the casting, the silica manganese slag is separated from ferroalloy, which is then classified as industrial waste and usually disposed with special attention. This is because in Malaysia, silica manganese is considered to be a scheduled waste under SW1 Metal and Metal Bearing Waste of Environmental Quality Act 1974, and thus disposal of scheduled waste are quite expensive. Therefore, rather than incurring expenses to dispose the waste, why not try to reuse and upscale these waste into something useful? Currently, there are a few existing alternative landfill liners that utilizes industrial byproducts as landfill liners, such as steel slags, blast furnace slags, and fly ash. However, there has yet to be any literature on the use of silica manganese slag as landfill liners, making this research project a novelty. The problem statement of this research project is that there is little literature coverage on the material properties of silica manganese. The importance of material properties in the pursuit of identifying its potential as a landfill liner is significant. This is because one of the most important properties that a landfill liner must possess is to ensure that it performs adequately and that it must be designed to have a low hydraulic conductivity, which is usually less than 1 × 10⁻⁷ meters per second in most standards. According to Shackelford, hydraulic conductivity is a material property that reflects the relative ease of liquid that flows through a porous media. Hence, in the case of landfill barriers, a low hydraulic conductivity is required to prevent the passage of leachate into the soil and groundwater environment. Hence, the aim of this research project is to explore the possibility of utilizing silica manganese slag as a potential landfill liner while meeting the performance criteria set by relevant standards such as ASTM and EPA. As of now, due to the movement control order restricting the use of the university's lab facilities, numerical modeling will be conducted instead via GeoStudio. However, the lab testing of material properties such as particle size distribution is conducted, granted if possible. After highlighting the importance of silica manganese slag in the performance of landfill liners, the hypothesis for the research project is that there is a possibility that silica manganese slag may not meet the hydraulic conductivity performance required by relevant EPA standards. However, the hydraulic conductivity of silica manganese slag can be improved with the addition of other constituent materials such as bentonite, a pure clay material that is widely used in the industry for its low hydraulic conductivity and high sweating capacity to form a composite landfill liner material, or to increase the liner thickness of silica manganese slag altogether. This research project is essential and significant as it eliminates the special disposal cost of silica manganese slag. As discussed previously, due to its classification of silica manganese as a scheduled waste that requires additional cost for its disposal, if proven successful to be upscaled as a landfill liner, this will instead translate to the reduction of waste disposed and possibly potential profit made if the silica manganese slag can be commercialized. This in turn encourages the practice of upscaling industrial waste into something that is useful. Finally, this research is significant as it reduces the reliance on natural resources such as clay completely, providing alternative composite materials to be used as landfill liners. For the literature review, the proposed components of the landfill liner that is selected to be replaced with silica manganese slag is the bottom liner section at Part A. Besides that, the drainage layer may also be a possible replacement with silica manganese slag at Section B. However, in this research project, only the bottom liner will be the focus for the use of silica manganese slag. The reason as to why the bottom liner is selected for this research plan is because the liner criteria to be qualified as a liner material would depend on its low hydraulic conductivity and high contaminant retention. Additionally, soil plasticity can also be a reliable indicator of hydraulic conductivity and contaminant retention characteristics of soil. In general, high plastic soils exhibits low hydraulic conductivity and high contaminant retention. In the case of silica manganese slag, there is literature about its potential use as an additive or complementary construction material due to its pozzolanic cementitious properties, naturally making the material an attractive use for a variety of construction applications such as concrete, similar to fly ash and steel slags. However, there is a lack of literature based on the hydraulic performance of silica manganese slag. Therefore, it will be interesting to explore the observations and performance of silica manganese slag as a bottom liner, as most existing industrial byproducts that were upscaled to landfill liners such as electric arc furnace slag, fly ash, and steel slag all managed to be evaluated as suitable materials to be used as a landfill liner or landfill covers depending on the recipe of the liner composite mixture. Thus, I have made a table which compares the specifications or criteria required by several standards. The important criteria that will be compared with the materials properties of silica manganese slag is hydraulic conductivity, liner thickness, and material content. Based on the standards set by EPA and ASTM, it is observed that the material properties of existing materials such as fly ash and steel slag performs well within the landfill liner specifications, which in turn will act as a point of reference for simulated results of silica manganese slag in GeoStudio. The methodology for this research project begins with problem identification. The problem faced is, as mentioned previously, the lack of literature on the material properties of silica manganese slag and its integration as landfill liners. Therefore, literature review is conducted on existing landfill liner materials, namely fly ash, steel slag, and electric arc ladle slag, which were experimented and had their performance as landfill liners reviewed. Hence, with the information collected from relevant literature, it is then compared based on landfill liner specifications or criteria based on the existing standards such as ASTM and EPA standards. Once sufficient literature has been reviewed, the numerical model begins via GeoStudio. To ensure that the numerical model is designed correctly, the first model developed is a simulation of a permeameter while referring to ASTM standards. The idea is to pay attention to the geometry of the model, its boundary conditions, and its results. This is to ensure that the modeling technique is validated, ensuring that the software is used correctly. Once this is done, the next step is to calibrate the permeameter model against typical specifications while referring to the standards and criteria set in article Geotechnical Aspects of Landfill Design and Construction written by Jasberger. It is important to pay attention to the seepage and the hydraulic gradient of the model through the drainage and the clay layers. This calibration is important as it will establish the baseline model for the research project. Based on the baseline model, parametric studies of the model are then conducted where the parameters such as hydraulic conductivity, layer thickness, and boundary conditions are adjusted and compared to the baseline model, which acts as a point of reference to the model. Parametric studies are important to identify their behavior and results if the parameters are changed, identifying the seepage or gradient performance. The current works for this research project is at stage 3, which is the development of a preliminary permeameter model. The figure illustrated here at the preliminary work section is the first drafted permeameter model that I have developed. To simulate a permeameter, the dimensions of the soil sample were set to be 5 by 3 meter and the height of the water is 2 meter above the surface of the soil sample. Hence, the boundary condition set on the permeameter is a constant total water head of 5 meter at the top of the soil sample, indicated in green, and a drainage condition at the bottom of the sample, indicated in white triangles. The vectors indicated in the model simulates the flow of water from the top of the sample, where water pressure is the highest, indicated in red, flowing through the sample and finally discharged via the drainage layer at the bottom of the sample, where the water pressure is the lowest, indicated in blue. At this stage, the modeling technique is validated, in which the next stage will involve calibration of the parameter model into landfill specifications set by EPA and vice versa, based on the flowchart set at methodologies. Upon completion of the research project, the future work set is to conduct field applications of silica manganese slag as an alternative landfill liner material, compare field performance of silica manganese slag with existing liner materials, and conduct further research on silica manganese slag strength enhancement. Before I end this presentation, I would like to express my utmost gratitude to Dr. Chu Chung Seong for the counseling and guidance that he has given me throughout my final year research project 1. Thank you for listening, and hence I conclude my presentation. Thank you.